Welcome, everyone, and thank you for joining us. This event will discuss innovations in efficiency, emissions controls, and fuels for internal combustion engines. During this event, all participants will be in a listen-only mode. To ask a question at any time, please submit your question using the Q&A box at the bottom of your screen. We encourage you to ask questions at any time. Questions will be addressed when possible. This event is being recorded. The recording and presentation will be available on the Engine Technology Forum's website shortly after this live event. I would now like to introduce our first speaker, Alan Schaefer, who's the Executive Director of the Engine Technology Forum. Alan?
Thanks, Josie, and good morning, good evening, good afternoon to everyone, no matter where you are. It's nice to have you with us. We appreciate you taking some time today to learn more about what's happening in the world of internal combustion engines and the fuels that they use. A quick word about us. The Engine Technology Forum really is an educational organization, and our hope is that we can, through venues like this and informational settings, provide you with some insight and perspective about the future of internal combustion engines, fuels, and technology. I want to thank all of our members for making today's session possible, and you're fortunate that you will hear from some of these members here during our session today. I just want to begin with a brief opening remark about what's the future for internal combustion engines look like, and how do we see that. Today, the internal combustion engine really drives key sectors of our global economy, from agriculture and industrial applications to public transportation, rail, and trucking. Internal combustion engines, those powered by gasoline, diesel, natural gas, propane, really are key to our current economy, and we see them also as a key part of our energy future. And that's because of several reasons, which we are going to get into today, and that is the increased efficiency of the technology, its ability to achieve even lower emissions, and the role that sustainable and renewable fuels play as part of this future endeavor. Today's session is going to look at three areas. First of all, the fuels, the quality of fuels that we're using, the type of fuels, and a focus on renewable biofuels. We'll also discuss the efficiency that's taking place in engines, components, and their fuel delivery systems, and how it all works together. And then finally, we'll talk about what innovations have occurred in emissions controls to help meet the tighter standards that are happening in the future. So that's the breakdown. We are fortunate to have with us today a great panel representing great companies, and we're going to hear from each of them in just a moment. We're going to begin with our session on fuels, and for that, our two participants will be Steve Howells, is the founding partner of M4 Consulting, and Steve is also chair of the ASTM Biodiesel Task Force, I should say longtime chair, and he really is the expert on fuel quality and renewable fuels. And we're delighted to have you with us today, Steve. And then also from Innospec is Mary Derry. She heads up their performance additives group, and we'll look forward to hearing from her just after Steve's presentation. So Steve, I'm going to kick it off with you, and welcome, and thank you for being with us.
Well, thank you, Alan, and thanks to all the attendees here today. I'm going to give you a summary of what's going on in the biomass-based diesel area in a low-carbon, low-emissions future. So next slide, please. So just to level set a little bit, we have two kinds of biomass-based diesel out in the marketplace today. Both fuels are made from vegetable oils or animal fats, renewable low-carbon feedstocks. The renewable diesel is made through a reaction with hydrogen, typical refinery-type reaction, hydrotreating and isomerization. It converts the 3-carbon backbone to renewable propane and then converts the oxygen to hydrogen. And that fuel is a paraffinic fuel. It's ultra low sulfur, it's zero emission or zero aromatics, it's high cetane, and it meets the diesel fuel specification ASTM D975. For biodiesel, that is done through a different process, less complex process, a little bit less expensive to make. That goes through a reaction with methanol called transesterification. It converts the 3-carbon backbone to glycerol, which goes into the chemical market. And the oxygen actually remains in the fuel, which allows the fuel to be biodegradable, non-toxic, and increases lubricity. That fuel meets a different specification since it's an oxygenated fuel and not a hydrocarbon. It falls under the specification D6751. And all those specifications are designed to make sure that the engines and the after treatment are going to last for the full useful life of the vehicle. Next slide. So a lot of folks may not really realize we use a variety of oils and fats to make biodiesel. Soybean oil is about a little less than half. It's the most prevalent oil, but we use all sorts of different oils and fats, distillers corn oil, animal fats, used cooking oils, canola oil. So there's a variety of oils and fats, with soybean oil in the US and in North America representing about half the market, and the others kind of spread kind of evenly throughout in terms of the rest of the volume of the fuel. Next slide. So folks may not realize, but in the early 90s, when we first started the biodiesel area, the main driver for using biodiesel and now more recently renewable diesel has been to provide an added outlet for excess soybean oil. When you grow soybeans, it's 80% protein and 20% oil. And there's actually, so people grow soybeans for the protein and not for the oil. And in the 90s, there was an excess of soybean oil, and biodiesel was a viable outlet to use that excess soybean oil. So that's really how the industry first started. And a lot of the effort put in was by soybean farmers. Next slide. So by creating a market for that excess oil, you actually make the food portion a little bit cheaper. So that was one of the other driving forces. And if you go on to the next slide, Alan, and folks may not realize, but you can't produce a gallon of biodiesel without co-producing 30 pounds of protein and 22 pounds of carbs and dietary fiber. So with biodiesel, it's a very sustainable market, sustainable industry for food and fuel. And when we grow protein to feed the world, you get more fat than we can eat. And so those byproducts can be used to make high quality biomass-based diesel. As long as we have people on the planet, we're going to have excess oils and fats that we can turn into usable, low carbon, high quality diesel fuels. Next slide. Some of the early driving forces were, for our industry, were energy security and economy. And over the past 30 years, we've seen those driving forces change. But those are still out there. Reducing dependence on foreign oil is not as important now as it was early on in the industry. But adding jobs, adding refinery capacity, those were all drivers for the industry. And the way that the industry captures those forces, go on to the next slide, please, is through public policies. Public policies have helped monetize those societal benefits of biomass-based diesel fuels, whether they're renewable fuel standard type credits, tax incentives, low carbon fuel standard credits. And those credits and those policies have allowed the industry to thrive. So if going to the next slide. So the industry has really increased in consumption particularly over the last 15 years. In 2010, we were making about 200 million gallons of fuel. Last year, we made over 4.5 billion gallons of fuel, and we've seen renewable diesel start to see market penetration. We're right around 50-50 renewable diesel and biodiesel in North America here today. Going to the next slide, that represents the 4 billion gallons we're producing right now, represents just about a little over 10% of the U.S. distillate demand and growing. So folks may not realize how much we've really progressed as an industry, and over 70% actually of the market in California is actually a combination of biodiesel and renewable diesel fuel due to the low carbon nature and that low carbon fuel standard in California. So folks may not realize how much our industry has progressed and the innovation that's happened in our industry. Next slide. So the driving forces for our industry are changing. The major driving force now is carbon. And when you look at biodiesel, biomass-based diesel, the energy from the sun grows and takes CO2 from the air, grows an oil or fat. We take that oil or fat, we burn it back into the air. There's a net life cycle reduction of carbon in the atmosphere about 70%. We assume that all of the energy used to grow and produce the fuel comes from a fossil source. So as we decarbonize the fuels and as we decarbonize energy, that life cycle CO2 decrease will approach net zero. Next slide. So we really look at biodiesel or biomass-based diesel as liquid solar energy because the energy from the sun is growing the fuel, and we store it in a fuel rather than a battery. So a very good, forward-looking industry. Next slide. So one of the factors that is really becoming more aware is the time value of carbon, or why reducing emissions now is essential. Because carbon builds up in the atmosphere. The carbon we release today is still there next year. The carbon released that is still there for the previous 2 years. So there's a compounding nature of carbon in the atmosphere. And for every 5 years of delay, we have to reduce 13 more carbon times more carbon emissions to have that same climate impact. So that's part of the reason why our fuel is growing, why we saw a lot of increase in our volumes over the last year. Next slide. So as we desulfurize diesel fuel, one of the advantages for biodiesel is it improves lubricity. The oxygen in the fatty acid methyl ester that is biodiesel actually improves lubricity. When we took the sulfur out of diesel fuel, both renewable diesel and conventional petroleum fuels need some sort of lubricity additive, and biodiesel can be that lubricity additive, and more lubricity would mean less wear on engine parts and fuel pumps. So combinations of the fuels are really taking off and really seeing market penetration. Next slide. So as we desulfurize that fuel, the engine technologies, which you'll hear a lot more about here over the remainder of this Zoom call, most of the emissions reductions now out of engines are due to the aftertreatment systems. And that sulfur reduction has allowed those aftertreatment systems. And we've designed the ASTM specifications to make sure that those aftertreatment systems are going to work long-term. And so every time we have a change in the aftertreatment systems or a change in the fuel, we go in, the industry does a bunch of research and work to make sure that the fuels that we've set right have the right ASTM specification to make sure that the engines are going to produce the emissions that they need, and that the fuels are going to last long-term, and that the aftertreatment systems are going to last long-term. So next slide. So we're actually doing that right now as an industry with the new technology coming down the pike, which you'll hear about more. This is just some examples of some work by Southwest Research on that new technology. And the net of this slide is that those emissions are reduced the same with B20. I don't have renewable diesel on the slide, but renewable diesel is in that same range. And so we're doing that work to make sure we've set the specifications right, and that those emissions are going to provide the same low emissions regardless of the fuel. Next slide. And one of the interesting advantages we may see in those new engines is we do reduce the particulate matter coming out the back of an engine. The tailpipe out's very low, done by the aftertreatment system, but out of the engine, we do see particulate reductions, and B20 shows a pretty large reduction in engine out, and that might actually reduce DPF regeneration frequency, which might have a long-term impact, positive impact long-term on those new systems moving forward. Renewable diesel is roughly similar to B20, so both particulate reductions. So we're actually looking at doing B50 and B100 standards at ASTM now moving forward. So the long-term industry vision is 6 billion gallons by 2030 and 15 billion by 2050. So we're looking to grow this industry. Next slide, please. And we have enough additional feedstock capacity to do about another 1.8 billion gallons right now. And we're looking at future expanding yields from vegetable oils, expanding domestic crush, expanding the used cooking oils and other products we use, novel applications. Over the last 100 years, since oils and fats are a minor byproduct of producing protein, the agricultural industry has tried to minimize the amount of oils and fats. So now that we have demand for low carbon fuels, how much larger could we be? And if that technology is turned on its head to say, hey, let's maximize oils and fats, how much larger can we be? And we're looking at doing that right now. So to kind of summarize, next slide, please. So the takeaway messages on the fuel side of the things, that there is real value in reducing the life cycle carbon now and not waiting. For every 5 years, we wait 13 times more carbon reductions needed. The new engine technology is going to reduce NOx and PM to near zero levels, regardless of the fuel. So tailpipe emissions are going to be reduced. And then the atmospheric carbon, the low carbon nature, you reduce that 70% today, and we're going to approach net zero, as the fuels and its power are decarbonized to produce the fuel. And our industry is doing the work so that B100, renewable diesel 100%, or some blend of the two will be viable options for low net carbon combustion in 2030, 2050, and beyond. So that summarizes my information for you. I hope you found it useful, and back to you, Alan.
Thank you very much, Steve. That is quite a story. As we all know that are working on these issues every day, the importance of sustainable, renewable fuels is a key part of the future for internal combustion. So thank you for that. Let's turn now to what's happening relative to fuel quality, and that is a key part of the whole equation here, both customer satisfaction of the engines as well as the performance and compliance with engine standards, et cetera. So here to share that insight with us is Mary Derry, and she is with Innospec. So Mary, welcome, and I'm going to turn it over to you.
Thanks, Alan. Can everyone hear me okay?
Yes.
Perfect. Hello, my name is Mary Deary. I'm the Director of Performance Additives here at Innospec Fuel Specialties. A little bit about our company. We are a global company. We have around 2,100 employees scattered across the globe. I happen to be in Newark, Delaware. We call that the Pencader site. And our focus really is fuel specialties. We've been making fuel additives for quite a long time, but Innospec also has two other divisions, one in performance chemicals, which is cosmetics, healthcare, personal care, as well as oil field services. Next slide. So as Alan mentioned, diesel, I'm here mostly to talk about diesel and heavy duty diesel. And over the years, they have lowered the sulfur content of diesel for good reason. That was creating a lot of acid rain. And ultimately, they reduced it to 15 parts per million maximum, with some off-road applications being able to use a higher sulfur diesel. But in reality, all the refineries are making the ultra low sulfur diesel. So generally 90% or more of all diesel is 15 parts per million all around the United States. And the impact of that obviously is lower SOx emissions, lower acid rain. And as Steve mentioned, there's the lubricity properties have changed, the oxidation properties have changed, and some benefits include less injector fouling and less particulate emissions in general. Next slide. But what we see as a fuel company are field issues, even with the ultra low sulfur diesel. So if you have an untreated diesel fuel, you'll get reports of filter plugging, gelation, and tank sludge. Next slide. And with that comes injector fouling, and you'll get quite a lot of deposits, not only on the outside of the injector, but in the little holes of the injector that sprays the fuel. And as you can see in that little picture on the right, the fuel is coming out as a direct stream. It's not coming out like an aerosol spray. That means your fuel is not going to combust properly in your combustion chamber, which leads to poor fuel economy. It ends up making more particulates, as you see here in the DPF. You'll lose lost productivity because you have to regenerate that DPF more often, sometimes in a parked idle format where the vehicle actually has to stop working. And doing that, you use a lot more fuel. You can click ahead. Next slide. And ultimately, you're going to use more fuel, which means you're going to create more carbon dioxide. You're going to get a lot more hydrocarbons and particulate matter. Next slide. But now with treated fuel, and treated fuel has many, many additives in it. There are lubricity improvers, cold flow improvers for winter months so that you don't get that gelation, corrosion inhibitors, and detergents, which are also known as deposit control additives, or DCAs. As a result of using a treated fuel, you not only can clean up injectors, but you can keep them clean. And what that means is those holes are remained open, completely open. And as indicated in that diagram, the picture on the bottom, you see a nice aerosol spray. That's what you want to see. You get better combustion, better fuel economy. You'll see less DPF deposits. So go to the next click. A DPF will be cleaner for longer. You'll use less fuel and ultimately less emissions all the way around. Next slide. Ultimately, detergents improve the fuel properties and return your engine to the factory design parameters that your OEM has designed your vehicle to operate at. Just a little bit about combustion so everyone understands why when I say if you use less fuel, you have less CO2 emissions. I'm a chemist, so I think in terms of chemical equations, but I'll keep it simple. If you burn a hydrocarbon in oxygen, have complete combustion, you only make CO2 and water. That is the most complete reaction. Click again. But in real life, you're not just burning oxygen, you've got air present and you make other byproducts. Click again. And in air, we have mostly nitrogen, and that nitrogen contributes to the making of smog or NOx emissions. That's what they're called. You also make carbon monoxide, which is highly toxic, as we all know. You'll get solid carbonaceous deposits, which are also known as particulate matters or PM, and as well as the CO2 and water. Next slide. Here's an example. We'd like to show how our fuel additives can improve performance in real life. There are standardized tests, but this is about some field trials that we've done in the recent years. In this farm tractor trial, we took a tractor that had over 1,800 hours on it and pulled the injectors. If you look at the untreated injector, you'll see that there's deep, deep caverns of deposits in there. Looks like a volcano. But after only 100 hours of operating on a detergent additive in the fuel, you can see that those deposits around the hole have eroded away. Click. And with that, we've reduced the NOx emissions 30%. Click. And additionally, we can reduce emissions by 30%. And as you can see on the PM 2.5, and that's particulate matter, that's 2.5 microns or less, which is very, very small. It's been linked to lung cancer and other pulmonary health issues. We have a 34% reduction there. Next slide. In another on-road vehicle test, we took a Sprinter van and we did a DPF loading study. And we took untreated fuel, ran it in a Sprinter van, and measured how long it takes to saturate the DPF, requiring it for a parked regeneration. We had to do some software modifications to make it do that, but we ran it twice. And as you can see, it's pretty repeatable. And that's just under 3 hours to load that DPF, requiring some form of regeneration. Upon adding a treated fuel with detergent control additive, upon the first treatment, we've extended it close to a half an hour, and subsequent tanks or treatments extended all the way out. After 4 trials, we stopped it. We extended the DPF load time by 77%. We could have ran it longer and longer, and maybe that's a future study, but just the fuel savings and just the regeneration there was a 1% fuel consumption improvement. Next slide. We have customers that are mining customers, and some of them have underground mines. So carbon monoxide emissions is very important to them. So in this trial, we ran 24 vehicles, and for 4 months, we ran them on untreated diesel fuel, ULSD. And then after 4 months, we switched them over to a treated, detergent treated fuel, and then monitored the fuel consumption again over 4 months, as well as the CO emissions. And as you can see in these graphs, we had almost a 5% fuel consumption savings and a 14% reduction in CO emissions. Next slide. Here are just, and some people think fuel additives are snake oil, and just so you understand, we run many, many trials, and this is just the trials in the Americas. We use statistics to measure the effect of our diesel control, detergent control additives. And as you can see here, we range anywhere from 1% to 17% fuel economy or fuel consumption reduction. We don't say everything gets 17%. Obviously, the average of these trials is about 6%. Typically, when we work with new customers, we say anywhere from 2.5% to 5%. And all that translates into carbon dioxide savings. Next slide. So what can an owner operator or fleet owner do today to save on CO2 to meet the new requirements? They can take their existing vehicles. There's no fancy technology required. They can use biodiesel in combination with a diesel detergent to get significant CO2 and particulate matter reduction. Next slide. And how that works is, and we heard a lot about this from Steve, thank you, this was a natural segue. If we look at the carbon intensity of a variety of fuels, you can see diesel and gasoline at the top, they're about 100, and biodiesel and renewable diesels are down by around 30. Of course, that all depends on how that fuel is made, where the feedstock comes from, what energy source they use. It's a bit of a complicated formula, but you can essentially save 70% in CO2 by switching over to biodiesel and renewable. So, next slide. If you combine the biodiesel or renewable diesel with diesel detergent, hit return, you'll have 50 to 70% reduction in CO2 with the biodiesel, another 3 to 6% savings with your diesel detergent, and now we're talking 80% reduction in CO2 emissions. Next. But let's talk a little bit, and this will go quickly, about renewable diesel. We've done extensive studies on renewable diesel because it's the talk of the town. We compare it to ULSD in a typical industry standard test called the XUD9 injector fouling test. And while it does perform better than the ULSD, it still does form deposits. You have a 40% nozzle fouling there. Similarly, we have a DW10B test. This is a Peugeot engine that uses a foulant in it to purposefully make deposits in the injectors. Now, here are 3 different HVOs. The orange HVO is doing just fine. There's no power loss, but the green and blue certainly aren't performing as well. The blue actually has a 10% power loss. So not all R100s are the same. Next. And in the Sprinter van, yes, well, if you remember, the last Sprinter van study using ULSD fouled in about 3 hours. This is 4 hours. Okay, that's better. It's performing better than the ULSD, but it does foul. It does saturate that DPF. So now if we add diesel detergents, you can see that we're pretty much eliminating any fouling in the XUD9 test. We're restoring the power even with the worst HVO. And in the Sprinter van, it takes a while for this to load for some reason. Did you hit it? Next. Oh, we have a pause.
Yeah, it's sorry. There we go.
There you go. No worries. We were able to increase that saturation time to 7 hours. Again, it's 70 to 80% longer, and in this case we have a 2.7% savings in fuel consumption. So finally, in conclusion, basically we all know that regulations are getting stricter, reducing emissions for all vehicles, but one can reduce emissions significantly through their fuel choice and adding fuel additives to reduce those emissions even further. Steve told us about renewable fuels volumes are insufficient to meet our needs today, but by using diesel detergents, you can help keep your engines clean and optimize your emission reduction as much as possible. And then the one last piece is renewable fuel, or R100 or HVO. It does cause fouling issues. It's not necessarily the best thing since sliced bread. Not all are the same, and diesel detergents will help keep their performance working wonderfully. So thank you very much for your time. I hope you learned something today.
Very good. Thank you, Mary and Steve, for that great discussion about fuels and also reminding us of all the chemistry that we either knew or thought we knew. But that was a great introduction. We'll come back for some more questions and discussion about the innovations in the fuel sector. But I think you can see from those 2 presentations that a lot is happening to ensure the future success of the use of these kinds of fuels in a whole variety of internal combustion engines. Just a quick reminder to everyone, you can submit your questions through the Q&A box on the Zoom feature here, and we'll address those either specifically as we go along or at the end during the during the verbal Q&A period. So send those questions right along in the Q&A feature. Okay, we've talked about the fuel. Let's get into the engine and find out what's going on in there with regards to efficiency and how we ensure the future of internal combustion. And for this part of the program, we have two experts with us. Welcome to Ivan Tate, who's head of the Technical Center at Fiat Powertrain Technologies. And welcome to Srinivas Gunturu, who is the Chief Engineer at Stanadyne. And Ivan, we're going to start with you and take it away.
Okay. Hello, everybody. So it feels it's a consecutive presentation for me, so I'm not going to go into our company's history or product range too heavily. But I will remind everyone, FPT is a global powertrain company. We produce nearly 500,000 engines a year, and also over 250,000 powertrain components, so transmissions or axles. And it's easily the most exciting time within our industry, I think, since its inception. You know, we've got a lot of options coming on the table, a lot of customer acceptance to those alternatives, regulations changing dramatically, and also obviously facilitated by technological improvements as well and availability. Now, as mentioned last time, the base engine, base combustion engine at least, retains a lot of importance to us as a business. It's going to be a prime mover for a number of years to come. And what I want to talk about here is really where we're going with that product. Now, the XC13, so this is a 13-liter 6-cylinder diesel engine. You can see here where it came from. It's probably doing the company a disservice saying in 25 years we've only got two or three bullet points there, but what we wanted to do was really show how it's evolved. So, you know, conceived as an on-highway engine, we made the step into off-highway in the early 2010s. There was an increase of power, dual-stage turbocharging. Then there's your heavy legislation changes start to come in around that time. It evolved into natural gas. And then as a company, we kind of recognized what was happening now. So the Coaster X concept, you know, we were really looking at sustainability, modularity, and flexibility of our products. And the XC13 is really the new generation here, and fulfilling a lot of those concepts that we put down. So if we look at the words of efficiency and next generation, you know, we need to look at sustainability. We need to look at compatibility with different regions, both from their missions and emissions requirements. Like Steve said, carbon is a huge interest, but along with all the carbon regulation, the criteria emissions are also getting squeezed continuously. And then we've got cost to manufacture, cost to service, you know, total cost of ownership, even efficiency could be power output, efficiency could be just low service prices and accessibility. So if we go to the next slide, I'll work through some of the items we've developed for this engine, try and give some thought, trade-offs for comment. Obviously, a lot of this is based around increasing performance, reducing fuel consumption, increasing productivity. So weight, particularly in on-highway, is important. Maybe for off-highway, you actually want more weight in a certain location, but sometimes it's not exactly where the engine is. And then braking power, again, very important, looking at the whole driveline as a system. So big step change in the material that we used, common for all the engines, including, shall I say, the H2 that we've also shown here in North America recently. Moving to CGI materials, you know, so this enables us to be lighter, but also more rigid. So that aids emissions and also the amount of cylinder pressure that we can maintain. Now, when we're designing the block and trying to remain modular, you also have to think about the machines it's going into. So, you know, we've got multiple locations to put the oil filter, to put the dipstick. It doesn't seem to be a big thing, but if you've got an engine ECU and you've got turbochargers and coolers fastened around that engine, it increases the complexity of the system. Friction reduction. So this is really key, and certainly where a lot of our development also had to go. You know, it seems easy. Take the bearing service, improve the materials, reduce the surface area, and modify the clearances to optimize the friction. But we're also looking at serviceability. So increased service intervals, increased load versus previous generations. So working with lubrication manufacturers and a lot of durability work needed to be done to actually make those benefits come and deliver exactly what we needed there. Along with that, you know, all of this system, whether it's the crank, whether it's the valve train, we're also looking at reducing rotating mass along with all these other actions that we're trying to implement. So the valve train itself, we need to make it lighter. There's lots of components there accelerating every revolution of the engine. There's a lot of friction, and also the loads are increasing on those components. So here, one of our biggest requirements was to increase the braking power of the engine brake. This, in part, obviously improves drivability, but it also approaches some of the other emissions that are becoming entering the emission spectrum. So we can't do a lot about tires, but certainly brake dust, brake components, items that are starting to be measured and are starting to appear on emissions charts now that the tailpipe emissions have dropped so heavily. We designed the block for smart auxiliaries. So you can see here, oil and water pumps, variable speeds, two-step or fully variable. This is really an expansion. And if you think back to the first viscous fans, it's really just an expansion of that. Obviously facilitated by the electronics industry, facilitated by having electronic control on the engine. And obviously the fans themselves, you know, for example, have also improved dramatically from those simple hydraulic systems. Looking at the controls, advanced combustion control and thermal management. So particularly in startup conditions, cold conditions, and transients, the benefits of the fuel injection, being able to control turbocharger, back pressures, exhaust back pressures, and change injection patterns, reveals the fact that, you know, we can increase power, but we can also meet emissions and fuel consumption targets while doing that. I touched on combustion earlier with the cylinder block and obviously combustion control, and then we have turbochargers. So we've designed this system for downspeeding, one of the biggest ways to reduce frictional losses in the engine and pumping losses. But equally, the VGT needs to be there for a lot of our applications. We're not steady state generators. We're trucks on the road. We're tractors. We're combine harvesters. All of these applications take a 13-liter engine, and the response, the output, the drivability, and even emissions during transient require EVTTs. We also adopted ball bearing technology pretty much across the board for most of these applications or studying them. Again, frictional losses and pumping. And this can only be really adopted when we've worked with the lubrication manufacturers, and we have also the cleaner combustion that enables us to run those bearings. Natural gas, the largest point here that we've introduced with regards to modularity is the EGR system on the engine, making it easy to implement, making it easy to package. There's been turbocharger developments. This, whether it's renewable or conventional natural gas or in mixtures above, this is a big way, or a very important way for fleets to adopt, meet their carbon goals very quickly. So these engines are on the market today. Step change improvements, particularly being able to increase the braking power for the trucks and improve that drivability. Okay, next slide. The next slide, this is an interesting project. I think it fits our topic here precisely. We're part of a Department of Energy funded project. We're working with Eaton primarily on this, supported by Oak Ridge and Tenneco themselves, and you'll see a bit later on, have developed an incredibly modular ATS system that we can work. So the project itself was to review low NOx and reduce greenhouse gas for highway vehicles, obviously looking towards future standards. The idea was to take best-in-class future technologies, anything that was practical for production within, let's say, a 5-year window, and review its capability and impact on the product. And equally, you can see in the top right corner there, we took 5 tracked emissions, the prime mover on many farms, and the then proposed low load cycle for certification. And we're using those cycles as both our baseline and our goal. The tractors are particularly interesting. They're both can work steady state, high RPM on PTO work. They can have very high transient capabilities, but equally, they also have some very low load emissions when they're used off season, because they're a large investment for the end user. A bit like taking a Class 8 truck to the supermarket. Just because you own it, that kind of work happens with the tractors on the farm. So this is a 3-year project. We're currently in year 2. We haven't closed year 2 and presented, so I'm just going to discuss what we achieved in year 1. This has already been published. We've completed the engine hardware, so we took a prototype XC13. We used many components of the natural gas EGR system, and we've also added a cylinder deactivation system from Eaton. So full authority. You can see the little diagram there. It's interesting in many ways, even if you're just interested in NVH. We've learned a lot about that. There was also a pump added to that EGR system, so we can change the capability at low speeds, low temperatures. And then we have the after treatment configuration. So the idea was to take all options, a number of different likely configurations. So you can see e-heaters, obviously dual SCR systems, looking at the very heavy reduction in NOx. So goal was 90% reduction in NOx versus today's standard. And then 10% reduction in CO2 versus the current baseline. So yeah, e-heaters, fuel burners, different combinations of after treatment, trying to reduce the Brits there, reduce the back pressure on the system. This is currently running down in Oak Ridge. It's running successfully in Oak Ridge, and I hope to come back and I can update you on year 2 in the future. Thank you all.
Great, thank you very much, Ivan. Lots of work going on there, and you can really see the level of incremental innovation and improvement that have taken place throughout the entire engine there. So that's quite an interesting story. Let's turn now to what's happening in the world of making propane engines run more efficiently and be prepared for the future. And for that, we have Srinu Gunturu, who is the chief engineer at Stanadyne. Srinu, good to see you again, and I'll turn it over to you.
Thank you, Alan. Good morning, all. Good morning, good evening, good afternoon. I know there are a lot of people from around the world joined. So my name is Srinu Gunturu, and I'm the chief engineer for Stanadyne. Just to give you an overall view of who we are, we are a fuel system company enabling the clean propulsion through engine innovation in the fuel system, bridging the gap to zero carbon and reduce the ICE carbon emissions now. And also, we pride to say we specialized in critical fuel and air system components off and on-road, off-road and on-road. And also, we are in the ICE propulsion for the low carbon liquid fuels and also gaseous fuels, including hydrogen. And also part of our bridging the zero carbon, we do a remanufacturing to help have the circular economy or the sustainable propulsion to have this global, to make sure that we provide to the industry and also to the market. And also we have a global presence overall to support the local markets around the world. With that, next slide. I know a lot of other people have already discussed some of the fuels like the bio and also liquid natural gas and also the diesel side. Now I'm going to talk about the liquid propane, which we believe that it's going to be a great alternative and also increasing the efficiency of the current liquid propane port fuel systems that we have that are available in the market. And also what we see that the direct injection is going to have huge efficiency improvement and also the improved emissions. As you can see that the propane is the octane rating is around 105. And if with using the three-way catalyst, and probably we can reduce even more on the emissions and also with less expensive than the diesel aftermarket systems. And also because of the liquid propane, you'll get into the near zero particulate matter emissions. And as you can see that we have identified that there are almost 73% of the 2023 model year vehicles utilize, this is only in the North America, utilizes the direct injection up from 37% in 2014. So this will grow even more to have such a direct injection in the off-road comprised like with the diesel or less efficient gasoline port fuel injection systems. So we were trying to, we were in this to be able to help to improve the efficiency of this liquid propane with the direct injection. Next slide. So with that, during our research and development, with the help of KTEC, who's our implementation partner on doing the dyno testing, and also we work closely with the Propane Research Education Council on working with them diligently to be able to bring this to the market. So we did develop a system that put it on GM platform, which is LIT engine, with no major modifications from a gasoline engine, directly changed it to the liquid propane. And we were able to convert and make some smaller modifications on the software and hardware, and to have some vapor lock inhibitor in the system in the application form to be able to help to fire this engine with the liquid propane with minor modifications on the gasoline engine from the OEM platform. Next slide. And this is just showing the configuration of the, sorry, go back. The LIT engine for the replaced with the liquid propane direct injectors. There are some modifications to the design on the propane pump and also the propane injector. We have a little more flow from the propane injector, and also we have made design modifications to be able to have eliminate the vapor lock issue that we have, and also smaller modifications, but the engine was operated as in the OEM form. And you can see the performance between the gas with the GM 2500. It's with the torque of the GM 2500 is around 460 foot-pounds. We go to the next one. With that, we had baseline the LIT engine with the gasoline, and also we modified the engine, as I said in the previous slides, with the liquid propane. With these modifications, we were able to test the performance of that LIT engine, and you can see most of the engine speeds, like the fuel system, was able to meet the baseline gasoline benchmark, or in some instances, you can see that we have a little bit higher in the performance in the region of like 3,000 and 3,500 engine RPMs. Next slide. To continue this development, we did not only just completing the performance comparison, we went ahead and did the dyno durability testing to see that this DI system will destroy the engine or the cylinder heads or any mechanical issues that will happen. We haven't seen any sign of abnormal mechanical wear or valve seat recession, or so any issues with the fuel pumps or fuel injectors while running for almost 16 million cycles or 15 million cycles on the pump strokes. And not only just running steady state, we ran transient cycle with different start-stop conditions, cold start conditions, as well as 55 to 65 miles hour cruise testing as well, to be able to see whether this technology was going to have an impact on the reliability or the durability of the engine, and also on the fuel system components. Next slide. So as I said, we did have some obstacles during the development of this DI system to be able to test it on a gasoline direct injection systems. So the main obstacle that we have was the fuel. Propane is gonna be becomes a gas at the ambient pressure, and it vaporizes in the system. And as I mentioned before, that we made design changes to our pump along with to the system to be able to help that vapor lock with the liquid propane. So for the delivery from the high pressure pump, so that the pump won't seize and operates at higher pressures, and so that we won't see that vapor locks. And also we have developed a system of fuel rail pressure relief, just in case if there's any vapor forming in the rail, which will help in eliminate that vapor as well, to release and attach it back to the chassis side. And also the injectors were designed to maintain targeting the base of the engine with some penetration and some mixture changes based on also improved upon the efficiency of the injector to get a little more higher flow to get better combustion of the liquid propane in the cylinder. Next slide. So the results on putting together, we have a propane direct injection system that exceeds the power or torque performance of the baseline gasoline engine, with a proven 250-hour reliability testing with different test conditions. And we do see that the liquid propane and direct injection emissions will be promising results compared to the diesel and gasoline. We do believe that this technology requires, as the emissions changing in 2027, and there are technology with the PFI, but this will improve the efficiency of the engine significantly with the current market. And in the conclusions, this direct injection is high efficacy and reliability, and this technology is ready for the direct injection. And also we were looking to see if there is a potential to leverage DME blend and renewable propane, working with the Propane Research Education Council on the renewable propane with the new technology to achieve net zero carbon emissions. To take this to the next level, we took the initiative and converting a truck to be able to modify as a baseline from gasoline, and with a 5.3 V8 engine, we're gonna convert the truck to a liquid propane. We are planning to complete the entire full-blown EPA emissions testing to prove that you will have a major benefit of CO2 and also a lot of emission reductions that you will see that our next steps to take this to the next level for the market. Thank you for this opportunity.
Very good. Thank you. Thank you, Srinu. Great look at what's happening in innovation there relative to propane. We're now going to turn to our third segment today, and that is one focused on emissions control. And we have Louise Arnold from Johnson Matthey here, who is a product line director at JM, and Nick Morley from Tenneco, who will be joining us in just a moment. We're going to start with you, Louise. Good morning, and take it away.
Thank you, Alan. So just a couple of overview slides. So Johnson Matthey, we work across a range of chemicals, processes, and catalysts to make sure that our customers have solutions to their problems, and that we continue to improve and catalyze the net zero transitions for everybody. Next slide. We've been around for a while, 200 years. About 50 plus years in the emissions control space, and we're generally seen as number 1 or 2 in our chosen markets. And we're a global company, as I said, with about 11,000 people worldwide. Next. So what do we do? So we try to always think about sustainability. We're driving down transport emissions. We're transitioning chemical productions to sustainable processes and feedstocks, so both very relevant in this area, transforming energy systems and really working on that really circular economy. Next. So today we're going to be focusing most on emissions control systems that for us sit in the automotive systems, but we also do components for fuel cells in terms of fuels themselves, sustainable aviation fuel, and also some of these renewable chemistries, working on either hydrogen or methanol and syngas to make sure we have the low carbon solutions. Next. So we have, I think, yeah, there we go, prevented roughly 20 million tons of pollutants every year, and about a third of the world's catalysts have been provided by Johnson Matthey. So we've been here through this evolution of improvements in engines and fuels, and what that means for the catalyst technologies and if you like, reactions that become available to us as we see this evolution. Next. So I'm going to say a little bit about gasoline as well as diesel, and Mary in her presentation did a lovely summary of combustion. And so when you combust hydrocarbons in air rather than oxygen, you get some very different, more complex chemistries coming out. And this is what's led to the legislation and fitment of emissions control catalysts. Why am I talking about gasoline and diesel differently? Because when you burn gasoline fuel, you burn that generally around the perfect lambda 1. So you have ideally that perfect match of available oxygen in your air intake with the amount of fuel you're injecting. And you naturally perturbate as the engine and the injectors fire to get that balance of technologies. So because of this, in a gasoline or similar type engine, we can have one catalyst, if you like, that does all of the oxidation and reduction chemistries all in one neat package. And these three-way catalysts have been around since the 70s, but they've continued to evolve. So as we've improved sulfur, not just in diesel, but also in gasoline, we've been able to reduce the amount of precious metals needed in these catalysts. We've been able to expand the window of other promoters that we can use to maintain the temperatures, or rather the performance over time. And as we've managed fuel economy faster or more aggressively, we now are using that fuel more efficiently, and that oddly can lead to a much wider temperature range. So we need catalysts that can both work at low temperature ranges as well as be durable to high temperatures. And this really is an ongoing challenge, in a good way, for us in our catalyst development. And also what we'll be seeing in North America shortly is the introduction of the gasoline particulate filter. Now, we know diesel particulate filters have been on diesel engines here for a while, and we're starting to see particulate matter requirements in the new EPA and California legislation that will start to bring filters in on the gasoline side as well. These are established technology for the European and China markets, so it's exciting for us to start seeing this application in North America. So if you move to the next slide. So we continue to develop. So what's a presentation on emissions if without some light-off curves? So if you see the black line, that's a product that's currently in the market. And then some of the new iterations and improvements that we're making. And particularly if you look at that pink line versus the black line, we are improving that light off. 14 degrees is a lot in our chemistry, particularly when the PGM, which is the active ingredient here that's doing the conversion of these pollutants. We've got NOx, CO, and hydrocarbon shown here. You know, we've actually taken a third of that, or 30% of that PGM down. So that's a big improvement on both the cost, bringing the cost down, and that in itself reduces the carbon footprint of the product itself, because platinum metals originate obviously from deep underground in very low percentages in the metal, in the rock ores that are mined. And now we're seeing, so we're reducing that costly and high CO2 footprint ingredient, and we're improving the performance at the same time. And these are catalysts that you can see have been aged to over 1100 degrees, so they're very thermally durable, and we're seeing great performance. So that's a whistle-stop tour of some of the innovations in gasoline. If you move to the next slide. Again, I've simplified this because we've had a lot of great introductions again from Mary and Steve talking about fuels, and again some of the after treatment designs Ivan and Shrinu have covered. So really we can continue to improve our formulations, our after treatment. We need to know what's going into the engine and what's coming out of the engine to know what we need to convert and what opportunities we have. And in some of the new legislations coming in around the world, not just in the US, we're seeing really novel innovations like electrical heating and mini burners. So that gives us some more confidence of the temperature is going to be there for us to do these catalytic reactions and really be able to clean up those tailpipes. We are getting to the point now that it's, you know, our laboratories have to be so clean and the analyzers so accurate because we are measuring so close to zero that it's really a challenge to be able to say whether new formulations are adding, you know, significant benefits. And that's why we focus as well, not just on getting the best package, the lowest volume, the best performance, but also at the right price, not only for the engine or vehicle manufacturer, but then also passed on to the end user. So we continue to develop these formulations. And as I said, as the inputs change, we can tweak what we put into the after treatment systems. So at the moment, the majority of systems we have here in North America are copper-based SCRs, but maybe we'll see a bit more iron SCR, because that, again, that the combination of iron and copper can do some more interesting chemistries in terms of the NOx speciation as it comes out of the tailpipe. So again, as we improve mixing techniques for the fuel or urea additives, again, that gives us opportunities to use the emissions control system more efficiently, more effectively. And we're continuing to work with our partners to make sure that we have the best solutions. So if you just give me one more slide, I think. So just a quick plug for other areas that we're working in: clean hydrogen production, and also after emissions control treatment for hydrogen internal combustion engines. We have the chemistry behind sustainable aviation fuels. So again, we're working with industrial partners for those. Storing and transporting energy. So how do we use methanol or ammonia to convert to hydrogen, for example, or to use as renewable energy forms, and also stationary emissions control. So a lot of engines now are actually being used as backup power for power grids, the oil and gas industry, and things like data centers. Because they really do have a large use of electricity. They do need a backup there to make sure your data is safe in event of a power cut or other issue. So I think that's a very quick roundup of some of the things that are happening in emissions control. And back to you, Alan.
Great, thank you very much, Louise. That was fascinating and another chemistry reminder there, but in a good way. In a good way. Our last speaker, but by no means least, in this session this morning is Nick Morley, and Nick is the engineering director for the Controls and Advanced Technology Division at Tenneco. Welcome, Nick. I'm going to turn it over to you.
Thanks, Alan. At Tenneco, yeah, we are a pretty large company, very committed to, as it says at the bottom there, taking the internal combustion engines to the next level. If you go to the next slide. We're a global company, nearly 66,000 team members, with nearly 20 billion in revenue. And we are very committed to the combustion engine, like I mentioned, but also being a partner for our customers, being the best manufacturer and distributor, integrating all of these technologies, particularly in the after treatment. It can be a complicated endeavor. So lots of trade-offs between the decisions made at the engine level can have an impact in after treatment and vice versa. So it's important that we are a partner. Next slide, please. At Tenneco, we produce quite a variety of products, a lot of different engine components, things that are being evaluated by our customers, like Ivan. He alluded to some of them. A lot of those engine technologies enable lower friction in the engine, which helps CO2, and among other things. We also produce a lot of after treatment systems in the clean air division where I reside, including SCR, particulate filters, integration, and dosing systems. Next slide. So today, I'm going to present some technology packages that take the catalysts that Louise had alluded to, and technologies that enable them to be optimized or operate, let's say, at the most optimized temperature ranges. And there's several ways to do that. These menus of technologies presented in front of you is a fuel burner, electric heater, dual dosing, advanced mixing. Burners taking the diesel or gasoline fuel, depending on your engine you're dealing with, combusting it, typically with a secondary air pump, because particularly in diesel, you'll need that oxygen to produce an optimized heat stream for the catalysts. Electric heaters are just that. They're typically resistive heaters, and they produce the heat, not quite as much power as a burner. And they can be a little bit more flexible in their applications. And of course, dual dosing with advanced mixing is taking the maybe an additional SCR catalyst, moving it to where the heat actually resides, which is typically closer to the engine. And there are some complex interactions that can result from that. Go to the next slide. So the first thing you think of with a fuel burner is, wow, that's going to really affect my CO2. And while, yes, it does burn the fuel, it doesn't necessarily have to have a negative impact on CO2. The main purpose of a fuel burner is to improve the light off that Lisa mentioned. In this case, the case shown on the top right, we have nearly 6 minutes improvement in a diesel application on commercial truck. And what that can do is enable our engine partners to operate outside of kind of your cold start thermal management modes of your engine. So if you think about it, the traditional startup sequence would have a cold start of the engine where it's operating in maximum heat up mode, and that can have a detrimental CO2 impact, but operating with a burner can enable them to turn that thermal management off. And then the result on the bottom left there, from testing that has been done, and does depend on your test cycle, but you can have CO2 neutrality with a nearly 90% improvement in NOx with a burner. Go to the next slide. If you're not comfortable with burners, electric heaters, if you have 48-volt architectures on your vehicle, can be a very elegant solution. It's I would say a more simple integration versus a fuel burner. And typically it doesn't have quite the heating power. Maybe one heater is maybe 1/4 of what a burner could be capable of. But particularly with hybrid applications, and plug-in can have near zero impact on fuel economy, just by the nature of the electricity being stored in the battery. If needed, you can apply multiple heaters per system. They can be more flexibly packaged, let's say, and be placed much closer to the catalyst that needs the heat. And in some cases, you can have pre-engine key on heating to kind of preheat your catalyst system before the vehicle starts. This can certainly help with some of those quick start applications, and further optimize your system. Go to the next slide. So moving away from active heating, you can move your SCR catalyst a little bit closer to the heat source, splitting the total SCR volume. SCRs are typically used, or are used in diesel applications primarily, but the same premise can exist for catalysts or with gasoline engines and three-way catalysts, moving it closer to the engine. It does offer a little bit challenge when you're looking at packaging, but from an overall perspective, it can be a beneficial choice because this is a known technology. SCR catalysts with urea dosing have been around for a long time, and dual dosing has been in the marketplace in some regions of the world. And it does allow for some flexibility in terms of managing your NO2 to NOx ratio. This can be beneficial in passive regeneration. So there are definitely a lot of considerations to be made. This can be more of a comfortable choice. Final slide. And as an integrator, our goal, like I said, was to present a menu of options for our customers. And there certainly are a lot of proven technologies, not only in the after treatment space, but in the fuels and engine realm, that can allow us to really meet our emissions targets both today and tomorrow, not just on vehicle, but even the total life cycle, which is very important and ultimately the end goal. But there are a lot of variety of applications that our customers require, not only the end users, but off highway, on highway, pass car. These are all very different applications with very different choices of technology. So it is important to provide that menu of choices. But I think we're very comfortable that any of these technologies in any combination should be able to help us meet those emissions regulations moving forward. So I think that's it, Alan. Back to you.
Great. Thank you very much, Nick. Appreciate that. Very informative there as well. I think we are having questions through our Q&A box, the Q&A system. There are a number of questions coming in, and we'll start taking those here in just a moment. I just want to reflect just for a second, this last presentation, Louise and Nick. I think those of us that have been in the business for quite a while remember back to the 2007 days when we were first introducing particulate filters. And I recall from us having a display case that we took to different events, that we had a giant sample of a substrate and particulate filter system there. And to look at the evolution that's taken place there. And then to hear you say, Nick, that SCR systems have been around for a long time. And I think back in 2000, when EPA first set those heavy-duty standards in motion, there was really not tremendous certainty about how industry would meet, or if they could meet these ultra-low NOx and PM standards. that were coming in the 2010 timeframe. And, here we are in 2024 and looking at, further steps down in terms of emissions. So I think it has been an incredible trajectory of continuous improvement. I did want to just ask you both a question about packaging, and I think, as things get more interesting here with different applications, et cetera, I think, just sort of reflecting again on that, back in the day, there was sort of a big system that was kind of strung out, you might say, a little bit. And now it seems like everything is smaller, more compact. How is that evolved, and what do you expect in the future? Are we seeing more of that? And what are some of the innovations there that are taking place in terms of packaging?
So I'll have a quick stab. So I think originally, or particularly when you're talking heavy duty diesel, which is where we've seen most of the innovation on packaging, those initial after treatment systems, I think we all, as an industry, were quite conservative and a little bit concerned and wanted to be able to access different components and making sure we had the right thermal treatment or controls, and they were bolted into existing spaces on the vehicles. And then as the after treatment system has become more integrated into the early system, the engine and vehicle design, we've been able to be more confident about our engineering controls, about the design of the catalyst and the durability. And generally, we've just been able to use that knowledge and that confidence and the upfront integration of the after treatment system into the original design process to just really, like you said, optimize and bring those volumes and those packages into a much more elegant, if you like, solution.
Yeah, and to add on to that, the original designs for mixers were typically large and clunky, and there's been a lot of iterations of mixer maturity that has really brought the footprint of those down quite a bit, and also improving the overall performance. And if you have a better mixing quality, then we need less of Louise's product, let's say, which, there's trade-offs to be had, but, there's also definitely a lot of areas in integrating on gasoline side on the hybrid spaces, which are being challenged with battery packaging, taking a lot of the exhaust space. So we're seeing a lot of innovations, not necessarily on the innovation side or on the emission side, but a lot of the packaging spaces like flattened pipes or very creative stampings, better acoustic performance out of mufflers with much lower volumes. So it is really across the board a challenge on packaging, because as hybridization is coming along, you're getting more batteries coming into play.
Indeed, and just not to keep picking on you two, but we have a couple of questions in this space, and I'll just bring one of those in. I know you're actually answering some of them online as we speak, but for you, Nick, or both of you, what's the benefit of a dual SCR, and can you install a DPF after the SCR?
So from a chemistry kind of cascading, yes, you can. You have to design if you're having a close coupled SCR system, you have to make sure you can only do NOx reactions in a reducing environment. So you're balancing that chemistry, and you use it differently at different temperature points and during the use. So you might use it more when you're doing a cold start operation. So it allows you to generate some heat and you get some NOx benefits. But then when you're warmed up system, your downstream SCR will be doing much more of the heavy lifting, because the chemistries and the oxygen and the hydrocarbon mix in that first catalyst are not going to be ideal. So you can, or you can put a sort of a more complicated cascaded SCR system after the oxidation catalyst. So there's all sorts of opportunities and designs, and it's really very sensitive to how the engine is operating and how the load cycles are calibrated to make sure that the after treatment system can manage the range of temperatures and chemistries with the right injections of urea or in some cases even fuel in to make sure we get that right temperature and oxidation mix.
Yeah, and
Okay.
from maybe a 10,000 foot view, that the double SCR allows for the first SCR to have a much lower catalyst volume, and so that it reaches temperature much faster. And so when you key on your vehicle, you're converting that initial slug of NOx, let's say, quickly, and then as everything reaches more of a steady state condition, you can maybe turn off that SCR. Maybe not 100%. It does depend on your cycle and how you're calibrating your system, but you can turn that one off and go back to your primary one. That's maybe more in an optimal SCR setting.
Okay. We do have questions in the Q&A box there, and I know some of our speakers are responding to those very specific questions, so that's great. I'll let you all keep doing that. I want to jump back to our fuels panel for a moment. I wanted to start with you, Mary, and just ask a question sort of, what have we seen in terms of the trends in fuel quality over time? And there was a specific question for you, I believe, in here about what the detergents are in a diesel fuel detergent system. Maybe you can expand on that a little bit.
Well, I would say with regard to the fuel quality is dependent on many things. It's dependent mostly on, how it's refined, and we don't always know how the refinery is running and what catalysts they're using and all of that. And then once it gets through the pipeline and into a terminal, it might sit there for some period of time, it might not, or if the fleet owner keeps it in a storage tank for a long time, that degrades the fuel. Storage degrades the fuel. It oxidizes, it picks up water, things like that. So in terms of detergents, they sort of act as, well, they're basic surfactants, right? And put them in a very small dose, and they're able to act, and I don't want to say give you the wrong idea, but it's the same principle as soap. When you wash your hands, you're going to have an aliphatic portion, and you're going to have a hydrophilic portion. So you have a water-loving and an oil-loving component of the molecule, and then it makes a micelle and carries away the dirt or the deposit. And so these are the kinds of molecules we're putting into the fuel to help get those things out once they have been combusted in your engine. We also put additives in fuel tanks too, to provide fuel stability as well. Our additives ensure fuel quality because we can't always control the quality of the fuel coming out of the refinery.
Very, very good. And I think one of the most impressive and sort of new areas for me, at least, understanding was the work that's being done for making sure that renewable fuels actually are up to snuff in terms of what their composition is and whether they perform effectively, how they perform in an engine, and whether or not there's a need for treatment there. And as you eloquently said, the answer is clearly yes. There's importance there as well. I think, Steve, on a question for you on the fuel side as well. I think you showed a lot of opportunity for growth in the sector, and we certainly see that as a key part of the sustainability of the internal combustion engine. There've been a few questions in the chat about how you see what's the upper limit and where coming from fats and other things. I'll let you respond to those specifically. But I wanted to ask a question about the sort of the innovation on the fuel side, and it looks like there's innovation going on. Is that just to make sure that you can meet the emission standards in the future, or is it just to prove that the fuels are going to be qualified to be used? What is how is that being worked out by the industry?
Yeah, well, as the chair of the ASTM task force, that's pretty much what we do, at the ASTM area, working with the fuel companies, the engine companies, regulators to make sure that, as engines change, as the fuels change, we confirm that the specifications that we have for our fuels are going to provide long-term durability and performance in the diesel engines and the system. So, over time, there's all sorts of research that's been done to make sure that we've set parameters for long-term storage life, that we set parameters for extremely low levels of fuel-borne metals. Metals can come in the engine oil that might impact after treatment, but metals can also come in the fuel. We use catalyst metals to catalyze the biodiesel reaction. So we've really honed in on what those levels need to be, and what those levels need to be for a lower blend, and then what they need to be for a higher blend. And we're evaluating that right now. If you're going to use B100 versus B20, do you need to have a lower level of fuel-borne metals? The metals are already very low. They've been decreased significantly over the past 15 years. So those are open questions that we're doing research on. And if those metals need to be lower for long-term after treatment, health and viability, then, we'll set those lower at ASTM. We just lowered the metal specifications for B100 intended for B20 to make sure that those are okay, and we're evaluating that for B100 use. So it's kind of a constant interaction between the engine companies and the fuel companies to make sure that the fuel specifications are going to be providing long-term durability of diesel engines and what people expect.
Great answer. I think this is so important, really, right? Because we want the experience of folks that go out and continue to invest in internal combustion engines to have that, that great experience where there's not issues relative to the performance of the vehicle that are linked back to problems with the fuel. And that the work that goes on at ASTM and standard setting and spec and keeping fuel well treated, I think these are all kind of key, oftentimes overlooked, I would say, innovations and important aspects of making sure that we've got, the kind of fuel quality that can deliver these incredible efficiency and emissions demands that we're having here in the future. I want to jump back into the engine section for just a moment as we get close to the end of our session here today. And Srinu, I wanted to ask you from your vantage point there, working on advanced injection technology, not just for propane, but for all fuel different types. I mean, how do you see the future shaping up there in terms of other fuels and technologies for internal combustion engines?
So, so for the internal combustion engines, I think what I see is right now is going to be the E100 as an alcohol as well, along with the liquid propane. And I see there is hydrogen is there, but I see that's because of the resources that you required, plus the complexity of the hydrogen fuel itself. I see a path for that, but I think it's going to be at least 10 years down the line that we do see the hydrogen ICE engines as well coming into fruition, comparing with the EV technology that we have. But I definitely see that the ICE is never going to die. ICE will be there forever. Just to make sure that I will probably be retiring. I'm in my 30s. I'll probably be retiring on ICE. I'll probably see ICE engines till 2070 or 28, or maybe longer.
Okay, well said there. And we're getting close to the end time here. We did have one question I thought might be fun just to entertain here, and that would be, what is how much do you think that we'll see for what % of electric vehicles in the heavy duty sector do folks think will be in place by the year 2030? Everybody want to render a guess on that? What % of electric vehicles do you anticipate by the year 2030? I will say that we just did our registration-based analysis this year, looking at vehicles in operation across the US. And I'm pretty sure our electric vehicle numbers for heavy duty trucks were less than 1%. It was a fraction of 1%, a small fraction today. So let's go down the list. Folks have a perspective on that?
Is this new vehicles sold or total vehicles?
What % of electric vehicles, and by the year 2030, so whatever happens between now and then, what % do you think will be electric at that time?
3%.
Okay.
So, yeah, Alan, for, it's not my speciality here, but we'd be looking at something like, 3 times what we have today. But if we start looking at electrified vehicles where there's massive efficiency benefits using existing technology, whether it's engines, driveline components, maybe there'll be a far bigger increase if everyone accepts, take a step towards efficiency and sustainability rather than find a hydrogen fuel cell tomorrow to fit.
Hydrogen
Okay.
internal combustion engines. Still need hydrogen though. So by 2030, in real terms, in engine development and vehicle durability terms, that's very close. And I think a lot of fleets and individual owner operators will be very cautious, because buying a new tractor trailer unit is a huge expense, and they tend to be quite conservative. So I'm with Mary. I think it's going to be less than 5%. I think there are going to be some early adopters, fleet trials, etc., promotion by the government maybe, that will drive some more adoption or a faster adoption rate, but it's not going to be significant by 2030.
Okay. Nick, how about you?
Well, I'll cop out on a number. I'll say it's more than some and less than all.
That was
Okay.
politically correct.
All right, Steve, how about you? Steve Howells?
I think what Nick said.
Okay, everybody's playing it cautious here at the end. Ivan, I think you sort of weighed in already on this, but Srinu, how about you? What do you think?
I mean, I'm not going to talk about. I'll just talk about personally. I think it's going to be very tough to have EV. So that's just my personal opinion. But
Sure.
I as I said, like there should be a huge gap of the bridge that this technology needs to develop on hydrogen, liquid propane, alternative fuels. That's definitely need to meet the not only net zero in 2050, even to meet the emissions by 2035.
Absolutely. I think that's where we're going to have to end it. And just from our perspective here, I think what you've heard today is really the tip of the iceberg in terms of how much innovation is going on in internal combustion engines and emissions controls and the fuels that they're using. Certainly not an industry standing still, but looking forward to meeting the next challenge, which is even lower emissions and greater efficiency. And I think we had a little fun of a last question there that was not representing any company views, I don't think, but I think we all feel like there's definite movement towards alternative technologies, but for the near term anyway, internal combustion engines are going to be the thing that carries us through. And that's all the more reason why we have the need for continued innovation in all of these areas. So I want to thank everybody for being with us today. You'll get an email that's going to give you a link to the event and the slideshow that you have here. And we always welcome your feedback. You can send that along to us at the email here on the screen. I want to thank all of our presenters today. Great job from you all. It's a long session, but I think very informative and covered a lot of ground. So appreciate everyone's support for that. And with that, wish everyone a happy day, a good day, and we'll talk again soon. Thank you all.
Thank you.
Thanks, Alan. Thanks, everybody.
Thanks, everyone.
Bye.
Thanks, everyone.